An artificial intelligence capable of passing the uniform bar exam, writing complex software from scratch, and diagnosing rare medical conditions is currently staring at a single, simple word, strawberry, and it is completely, hopelessly baffled. Ask this multi-billion-dollar neural network to count the letter R in that word, and it will look you in the virtual eye and confidently insist there are only two. This is not a glitch in some cheap prototype. It is a fundamental blind spot built into the very architecture of modern artificial intelligence. For the past few years, the public has been told that we are on an inevitable trajectory toward artificial general intelligence. We watch these models solve advanced calculus, write poetry in the style of Shakespeare, and translate languages in real time. Because they speak so fluidly, we naturally assume they read the same way we do. We treat them as digital brains, processing the world word by word, letter by letter, slowly building an understanding of human language. But then, a simple internet prompt broke the illusion. Users began noticing that while these systems could write an essay on thermodynamics, they could not perform tasks a 7-year-old child handles with ease. They could not reliably reverse a simple string of text, write sentences where every word starts with the letter M, or count the letters in their own outputs. Critics leaped on this, claiming it proved these systems are nothing more than stochastic parrots, fancy tape recorders mimicking human speech with zero actual understanding. But the truth is far more fascinating. The model is not stupid. It is literally blind to the alphabet. To understand why this happens, we have to look through the eyes of the machine. When you look at the word strawberry, your brain instantly registers 10 individual letters. But an LLM never sees letters. It sees tokens. Imagine you are hired to translate a library of books, but you are forbidden from looking at individual letters. Instead, a machine chops every word into solid, colored plastic blocks. The word strawberry is chopped into just 2 blocks, a blue block representing straw and a red block representing berry. To you, the word is not 10 letters. It is simply blue plus red. If someone asks you how many curves or straight lines are hidden inside those solid blocks, you cannot count them because you cannot break the plastic open. You can only guess based on how often people talk about those colors. Why did the creators of these models build them with this bizarre limitation? The answer is a simple trade-off between power and money. If a neural network had to process text letter by letter, the computational cost would skyrocket. Every single letter would require its own mathematical calculation. A long document would require billions of additional operations, making the system incredibly slow and prohibitively expensive to run. Tokenization is the ultimate compression shortcut. By grouping letters into common chunks, AI laboratories compressed human language by a factor of 4. It made training these models financially viable, saving billions of dollars in electricity and hardware. But in doing so, they traded away the machine's ability to see the spelling of the very words it generates. This reveals a massive misconception about how AI works. Most people assume that because a task is hard for a human, like university-level calculus, it must be hard for an AI. And because counting letters is easy for a child, it should be trivial for a machine. But in the world of neural networks, this logic is completely inverted. Advanced mathematics is a highly structured language of patterns and symbols that map perfectly to token structures. The model does not struggle with calculus because it can navigate those high-dimensional mathematical pathways through pure statistical association. But letter counting requires the one thing the model does not have: direct, uncompressed sensory perception of the characters. It can solve the math because the math is made of blocks. It fails the spelling because the spelling is locked inside the blocks. This structural blind spot is not just an embarrassing trivia failure. It is a major bottleneck for advanced reasoning. It limits the model's ability to write perfect computer code, solve complex logic puzzles, and avoid hallucinations. To break through this wall, the industry had to design a completely new class of systems: reasoning language models. Instead of blurting out the next token immediately based on pure probability, these new models are forced to think before they speak. They use their internal monologue to systematically spell out words, letter by letter, in a hidden workspace before delivering the final answer. They are effectively wearing glasses to finally see the letters we take for granted. The strawberry paradox shows us that artificial intelligence is not a mirror of human intelligence. It does not think like us. It does not see like us. and its brilliant successes and bizarre failures are both side effects of the same alien architecture. When we ask a machine to count the letters in strawberry, we are not exposing its stupidity. We are exposing the clever, invisible shortcuts we used to build it in the first place. The next time you chat with an AI, remember, you are not talking to a human mind that is occasionally foolish. You are talking to a mathematical optimization engine that is slowly learning how to see.